Okay, so we're going to show something along the lines of what we showed for vector fields in R3. We're just going to do it in R2, and namely that path independence relates to this green operator. The hint says let's use something similar to what we did in R3, and let's just remind ourselves how that worked, and here it is. First, we set up a picture like this, and we say, let's suppose we have some surface with a boundary curve made up of two chunks that we're going to orient in such a way that these two chunks of curve have the same boundary points, and therefore they have opposite orientations as when thought of as part of the boundary of S. Right. So we're going to do the same thing now in R2. Okay. All right. Having done that, we're going to write down, here's Stokes's curl theorem. That was our foot in the door for this argument in R3. We're going to write down Green's theorem instead of Stokes's curl theorem, as the problem suggested, and then just note that we can rewrite the boundary line integral as a difference, and then make an argument about things being zero. So anyway, that's what this is referring to, and I'll let you guys read those details. Let's see here what I said. Okay, so let's do this. So we're in R2. Here's our region R, and let's say we have 2 points on that curve, and let's view this as being the curve C1, and let's view this as being the curve C2. Cool? Okay. Note that the boundary of C1 is equal to the boundary of C2. Same points, same orientations on those 2 points. Okay. Note also that the boundary of this region R is C2 minus C1. Because it's counterclockwise around R, and so it's positively oriented C2, but then we go backwards along C1, and that's a minus sign. So, okay, so let's write down, yeah, go ahead.
So we start with orientation counterclockwise.
When you say the boundary of R is a positively oriented region by assumption, then boundary means counterclockwise. So that's why counterclockwise happens coincidentally to be the direction that C2 is going, and that's why we put plus here.
Okay, that's why the negatives.
But as part of the boundary of R, we need to go counterclockwise, which is the opposite of the direction C1 is going, and this minus sign means just take that curve but orient it in the opposite way of the way it was oriented, by definition. And again, there's no way to avoid a minus sign. You're either going to have a minus sign there or there. Take your pick. And you can't get rid of both of them. So I think it's nice to have these curves, since this is how we're going to use it. This result about path independence is about two curves that have the same boundary. I think it's better to set it up this way. Some books will set it where this curve goes backwards, and then they have a plus here, but then they have a minus there. It's just weird. Okay, so here we go. Let's write down Green's theorem. Green's theorem says that double integral of green f dA over this region R equals the integral around the boundary of R of f dot dx. Green's theorem, right? Now, as the three-dimensional example, I'm going to look at this boundary, remind myself that that boundary is made up of two different pieces, and rewrite this as integral over C2 f dot dx minus integral over C1 f dot dx. Right? And what I want to do now is look at this equation. Right? Okay, so let's consider cases. One possibility, suppose that green f is 0. By 0, what I mean is the zero function. It's just flat equal to 0 everywhere. Well, if it's equal to 0 everywhere, that means that no matter what region R you pick, no matter what region, this integrand here is always 0, so certainly this double integral is always 0, which means that this difference is equal to 0, which means that these two line integrals will always be the same. And namely, what that means is if you have any two curves with the same boundary points, then their line integrals will be the same. Now, I'm going to let you write that down, right? But the point is there's a line of reasoning there that we just talked through that gives you that f is path independent.
So the line integral would always be the same no matter how long is one curve, or like no matter.
Yeah, I mean this one curve could go off and do all sorts of stuff over here as long as it starts and ends at the same point as C1. Yeah, that's just kind of amazing result. I mean, but again, don't be too impressed. I mean, ultimately we know that all of these vector fields are vector fields that are gradients, right? So ultimately all this boils down to is, for example, let's suppose you start here and you end up out in, I don't know, Raleigh. Whether you get to Raleigh from Duke by, taking the Durham Freeway and the 40, et cetera, or hypothetically, instead, if you get on 85, take 85 north, grab onto 95, take it, I think that goes all the way to D.C., and then you could drive along the beach all the way south and then come back along some little country road. If you end up in Raleigh, your total altitude difference, same, right? It doesn't matter the path you take, how long it is, how circuitous, whatever. If all you're keeping track of is altitude differences and altitude changes, yeah, it doesn't matter what path you're picking. And I claim all of these kinds of examples are kind of like that in some sense, because as we've seen before, all path-independent vector fields are gradients. So they're just keeping track of changes. So, yeah. Now, turning the argument around, of course, now you have to go the other way of two, of course. So suppose your vector field is path-independent. What does that mean? Well, if it's path-independent, that means that these two integrals are always equal, which means that this difference is definitely 0, which means that this double integral has to be 0 no matter what region you pick. And that can only be possible if this function, green f, is equal to 0. Yeah, so I'm going to let you guys fill in the blanks. We kind of talked through it, but I'll let you write that down.
So in R3, you use the Stokes.
Yeah.
Equals 0.
That's right.
R2, you use 3 equals.
Yeah, just exactly. And so these really are very, very similar arguments. So a good little exercise would be to look at what we just did here and then look back at this line of reasoning here and note that they're really morally the same, right? Yep.
Then
All
for
right.
surface independence, it's divergence.
Yeah, it used Gauss's divergence theorem. That's right. And then, again, very, very similar. Now, they're dimensionally different, right? I mean, it's surfaces instead of curves and solids with boundary surfaces instead of surfaces with boundary curves. But, I mean, yeah, other than that dimensional shift, morally identical. Yeah. Yep. All right, let me stop this.